Okay. Thanks for inviting. Today I'm going to actually demonstrate a way to build Web2 applications, especially browser Web2 applications using ZK virtual machine. And in particular, ZK WebAssembly virtual machine that are built by the Definite Lab. And I was the founder of Definite Lab and the main contributor of this ZK virtual machine. The agenda of this talk is split into 5 sections. At first place, I'm going to introduce a little bit about the WebAssembly bytecode. And then I will going to introduce the way to integration of ZK WebAssembly emulator with browser applications. And then I will demonstrate how to develop a tiny, fully on-chain game on top of our virtual machine. And by demoing that, I'm going to introduce a standard programming model. It's called MVC, so that which perfectly fits our architecture. And then I will introduce our proving service, which is WebAssembly ZK Virtual Machine Cloud. Okay, let's start. So, what is WebAssembly? WebAssembly is an instruction set architecture, so which is a binary encoding format that can be run by WebAssembly virtual machines on any hardware or software that supports this ISA. And especially this can be run in browsers. So which leads to our current discussion about how to actually port in WebAssembly applications in browsers into a ZK WebAssembly virtual machine application. And so far, the WebAssembly bytecode is now supported as backends for most of the traditional languages. For example, JavaScript, C, C++, Rust, Swift can all be compiled into WebAssembly and it runs in the browser. Okay, so what we can do using WebAssembly in the browser, I mark all these orange color titles to be the applications that we are interested at. So we can build peer-to-peer applications, especially games, in a browser, and building music applications, streaming and caching applications in browser. Also scientific visualization and simulations in browser, and definitely fat clients for enterprise applications, especially database and database services in browser. And outside browser, we can use WebAssembly to distribute game services and build hybrid native applications on mobile devices and symmetric computation across multiple nodes. For example, Substrate utilize WebAssembly virtual machine to build their chain facilities. And how WebAssembly can be used in browser applications is that modern web browser applications and browsers these days can natively support running WebAssembly. That means we can use WebAssembly and embed WebAssembly in the browser as the main logic, and the UI and the UI UX remains written in JavaScript and HTML. So today, my main target is trying to demonstrate how to separate the logic of a browser application so that we can replace the logic, the main logic with WebAssembly, and then run WebAssembly in our ZK WebAssembly virtual machine to generate trustless computations in the browser. Okay. Before we have introduced about what is WebAssembly bytecode and how we use that in the browser, now I'm going to introduce a little bit about ZK WebAssembly. The ZK WebAssembly is a ZK virtual machine that supports WebAssembly bytecode. It has 3 main functionalities. First, it actually runs the WebAssembly bytecode and generates proof and generates results. And the second, that it generates the same result as other WebAssembly virtual machines, just like the browser did. So that means it generates the same result as the browser did for WebAssembly. And the third thing that the ZK WebAssembly virtual machine not only generates the result, but also provides the ZK proof, which actually proves the correctness of the result of the execution of a WASM binary. Okay, and this is a brief of the architecture. So to integrate a ZK virtual machine in a browser application is a little bit subtle, and I'm going to review the classical application architecture of how we build a Web 2.5 application in old school way. So first we can see that the application is run separately outside the blockchain. If you actually run the application in the browser. And the application triggers on-chain data modification. And then this on-chain data modification gets signed and posted to the blockchain. This is a very efficient but less secure way to do applications because all the computation in the application side is not trustless, right? You depend on some centralized servers to actually sign the transactions and sign the logic so that it conveys the on-chain contract that a certain kind of logic has been carried off-chain. Okay, how to make this architecture a little bit more secure? And the idea is that we would like to put everything on-chain. For the first try, would like to put everything on-chain. So after that, the architecture will look like this, which we embedded all the logic on-chain. That means if you would like to do a complicated UI UX application, you have to sign all the transactions every time you modify and play a certain application. For example, a game, you move right, move left, every movement you have to sign that, and then you upload your transaction to on-chain and update the on-chain state. The problem of this fully on-chain application structure is that it's not very efficient, and it actually involves lots of signature, which actually triggers lots of gas cost. So, which is definitely not fit for certain applications like gaming. So our solution is that we still would like to have an effect of trustless for the on-chain application, but we're using the ZK technology, which actually transforms the logic part, not on the blockchain, but in a ZK virtual machine. So that in a ZK virtual machine, every time we interact with the application, we emulate and prove the result in the ZK WebAssembly virtual machine, and then push the state diff with proof to the blockchain and do the settlement afterwards. Okay, so regarding this architecture, I'm going to demonstrate how to do that, because at first glance, people might think this is too complicated, but actually it is pretty simple if you're using the correct tooling. Okay, I'm going to demonstrate a small card game, which runs in our WebAssembly application sandbox. And here, we are going to load a small game, which is a very dumb, trivial card game. On the left-hand side, I'm the player, and on the right-hand side is the monster that I'm going to defeat. So just imagine that in our Web 2.5 world, this logic is running off-chain, right? Untrustless, run off-chain, and every time we play a card, like we strike, it actually decreases the HP of the monster, and it's calculated off-chain. But what's the difference now is that we not actually only run this in a browser environment, we also run this in a ZK WebAssembly environment, which is the sandbox of this demo. So that if we perform lots of transactions, you see that we're not going to sign every transaction all the time, but every time we click anything, play and click anything, this is run, sorry, I get killed. But anyway, this actually finishes the game. So it might involve lots of transactions, but we're not going to sign all the transactions during the play. But what we do is that we have a sequence of user inputs. And because this game is can be run in a ZK WebAssembly virtual machine, we can generate a proof for the game. For example, we can submit and generate a proof. So if I click confirm, it signed all transaction for me and then push the execution trace to a proof generator, which actually generates the proof of the gameplay to a cloud proof generating service. Okay. So it's actually loading task. So this is the new task that we have just submitted. And this cloud ZK-WASM proving service will generate a proving for our gameplay. And after we get that proved, it might take a few seconds, maybe 10 seconds or 30 seconds. No, to maybe take longer. It depends on the trace and circuit size regarding how much time it will consume. So once we have done a proof, it has been done now. Once we have generated a proof, we see that all the inputs actually represent the gameplay that the users have performed on this game. And we generate a zk-SNARK proof, which can be used to convince the on-chain contracts that this kind of game is executed in a zk-WebAssembly sandbox. And the execution trace and the result and the reward is somehow calculated securely and trustlessly. So we can use this proof to verify on-chain. Okay, select the chain. Let's see this one. And we can, so sorry, maybe I have to connect to my wallet. Okay. So we can actually verify this proof on-chain and do some kind of settlement. Confirm, do the settlement. And you can somehow automate in your settlement contract to decide what kind of reward you are going to give a player after he have finished a long sequence of gameplay. For example, you can design a game, which is a SLG, and after 1,000 steps of gameplay, you can give him some rewards. And this contract demonstrates about how we can coding the callbacks once a proof has been accepted. For example, if someone would like to give a token transfer, if someone has finished a very good gameplay, he can write a verify function which actually verifies the proof at this place, and then call the side effect function. And based on the core data that the user has pushed to the blockchain, he can decide what rewards he could pay the player. So these side effect callback functions are the key to actually reward the user or give feedback to the user. And there are several good points of using this architecture. Firstly, you do not have to sign every movement of your gameplay. And the second thing that it's very smooth, and because it's running natively in the web, in the browser, that means you can coding a Web3 application just like you're coding a Web2 application. You can using JavaScript, Rust, C, C++, and then compile them to the WebAssembly and put your game straightly on a browser application, WordPress, in any kind of cloud service, and run the game, ask the user to play the game, generate a trace, and generate a proof. Because all the execution is performed in a ZK virtual machine, there's no security issue, right? And there's a small subtle thing that at the beginning I asked you to log in your wallet and assign an address, which means every time you play a game, you log in with a local generated signature. And this signature will be verified every time you push the proof to the on-chain verifier, so that no one can actually fake the gameplay and get your rewards. Right. Okay. So this is a complete front-end demo about how to use the WebAssembly virtual machine and embed your application in the browser. But there's another part. It's about how you actually coding your application, right? The coding application is not just putting the sandbox and adding some code just straight in the browser HTML, right? You have to coding your game logic in a WebAssembly. That means you have to pick a language that can be compiled into WebAssembly bytecode. The alternatives will be the JavaScript, the TypeScript, the assembly script, definitely, and the C, C++, and the Rust. In this demo, we use the Rust as our development language. And let's see how the game is developed. By the way, when we actually developing this demo, we're using architecture called MVC, which somehow separates the view and the model. And what we are interested in is that we would like to run the model and the controller in the WebAssembly virtual machine, but not our view, right? But the view, because the view is a representation of the model itself. And it has no point to actually prove the view for the on-chain verifier. So we mainly focus on the model and the controller. OK, here is how we coding the game. Let's first see the makefile, because the makefile sketch out the deployment of our gaming this time. We see the first line is the compiling command that actually compiles our full code into a WebAssembly package, right? So after we compile this, we see that in the package folder, we have our target files. It contains the main WebAssemblies and the type definition of our WebAssembly and the loading script that we can use to load the WebAssembly in the browser application. So we copy all these files into our React web application. And we copied it here. OK, we copied it here. And after that, we coding the controller using a tool called React. It's pretty simple. You put some buttons and add some on-click event handlers for the controller, which gives you some kind of callback when you actually click this button. Click. OK. So when you actually click this button, I think it picks a card, right? Here. You click the button, you pick a card. So what does the pick card mean? Because this is a controller, right? It has to call and interact with our WebAssembly. So that means this controller will eventually call into our WebAssembly code. And this pick card looks like this. Pick card, right? And see this init as any, and this is the WebAssembly so that we have loaded. This is the WebAssembly. So the pick card means you somehow get the handle of the WebAssembly you have just loaded, and you play a card, right? You play a card. It's pretty easy, right? So now this demonstrates that how we can load and interact with the WebAssembly image in our browser application. OK, now the most interesting part is how we coding the WebAssembly. So how we lay out and coding the WebAssembly so that it becomes an interesting application. For the applications that I'm demo at the moment, is a simple application, right? It has a global state and some activities that I can perform to actually change the global state. And if actually I win, I can somehow generate a proof and tell the on-chain contracts that okay, I have won this game, please give me the reward. Okay. So let's see how the game is coded. Because all this WebAssembly has to be run in a ZK virtual machine, we have to specify entry point of the image. And this entry point looks like this. The entry point calls the ZK main, right? It's just relevant to a main function, but we call it ZK main because the ZK virtual machine will run this and generate the proof of this entry function. And besides the core command handler, we have some signature handling stuff, which asks the user to actually sign the contract once they have finished a bunch of play. The core feature is that we perform the command in the loop, right? So in the loop, we somehow collect the command from the user. That means every time we click a button, the handler will somehow transform the command and transfer the command into the WebAssembly handler. And the handler will actually catch this command and perform the state transformation internally in our Rust code. So that means, just remember, in the Rust code, you have a large global state. And the handler actually performs all sorts of commands and change the global state. And every time we somehow change the global state, you still have to render the user, right, based on the global state that you have changed. So that gives another issue that we have to face, which is actually get the information back from our WebAssembly code. So somehow get a global state. And this is pretty straightforward because we can transfer the global state as JSON to the UI UX. You see that, okay, here is the global state. We have lots of features like how many cards it has, and if I actually play one card, I get another global state. So that the procedure will be I play a card, which actually triggers a command, and then which invokes the WebAssembly application. The WebAssembly application somehow handles the command, performs the command, and changes the global state. And now the UI UX somehow receive the global state back, and then render the application again, right? After several play, you reach a global state which is stable, and you can say, okay, I have finished my gameplay. At that stage, there's no signature happening, right? But if you're happy with the gameplay, you can somehow generate a proof, right? Just like what I have just done before, I think 10 minutes ago. And at this place, you somehow sign gameplay and generate a proof from our WebAssembly cloud. Okay. See, there's a new proof generating at the moment. Okay, that's the whole story of the game development. And after that, I'm going to introduce slightly a little bit about our zk-WASM cloud. Because we have seen that once we have finished the gameplay, we need some kind of proving service, somehow generating proof for the ZK virtual machine. And you can run a ZK virtual machine locally, just download our GitHub repo and set up a local server. It's fine. But for the cost effectiveness, you would like to integrate with the on-chain stable service so that you can submit your image, a game image, to the cloud. And every time you would like to generate a proof, you ask the cloud to generate the proof for you. And this is the WebAssembly image hosting and proving service. And it's pretty simple to actually uploading an image to the cloud service, which is just a one-line code. We call it publish. It's pretty simple. You download our SDK and connecting with our cloud zk-WASM service and provide the WebAssembly you have just coded and would like to play in your browser. Specify your private. Did this record it? Okay. And then let's run that. So because I have already run this script before, so it will give me an error that this WebAssembly image has been uploaded already. But if you have not actually uploaded this image, it will give you a WebAssembly MD5 code. And you can use this code and inject this code into your configure so that the gameplay can somehow know which image you are regarding to when you would like to generate a proof. And this is done in the configure file. So just copy that MD5 to this configure file, and you will get this small on-chain, fully trustless, off-chain game for Web3, which means theoretically you can turn every web applications into Web3 trustlessly using the WebAssembly ZK virtual machine. Thanks.